Hey everybody. Some of you have been asking me about some questions on page 71, and I thought maybe this is something that might be good for me to share with everyone. So here's the first one that people have been asking about. And the problem really seems to be, how do we deal with this thing? Because it's what we call a complex fraction. The numerator or the denominator or both contain expressions that are fractions. So how do we deal with this? It's going to get messy when we do the limit process. So is there a way that we can deal with this to simplify things, maybe before we even start thinking about computing a limit? And the answer is yes. And by the way, if you don't know this trick, don't feel too bad about it. It was probably something that was taught in high school when I was a sophomore or a junior, and instead of paying attention, I was probably out drinking a beer somewhere or something like that. But what I'm about to show you, I didn't know until I started teaching. So if you don't know this trick, don't feel too bad. I didn't know it either until I started teaching. But it's a nice trick. It's one that we should put into our repertoire of tricks and into our repertoire of knowledge. We have a complex fraction. And what we do is we look at the denominators of every term in the numerator and every term of the denominator. This term has a denominator of 3 plus x. This term has a denominator of 3. And this term, well, I don't see a denominator here. It doesn't mean that there isn't a denominator here. I just don't see one. But isn't this really x over 1? So I'll put 1 as the denominator of this term. Now, we've all heard about least common denominators. That's not necessarily what we're going to get here, but it's not necessary that we have a least common denominator. All we need is a common denominator. And we can get a common denominator just by multiplying the denominators of every term together. If we multiply the denominators of all of the separate terms together, we get a common denominator. And here's what we do. We multiply the top of the fraction and the bottom of the fraction by the common denominator. And you're probably thinking, well, what good will that do? Well, just watch. Excuse me for a minute. Sorry about that. There was some noise outside. I decided I could do without. I'm in the process of multiplying the top of the expression and the bottom of the expression by the common denominator. This is the box that lists the steps that I take or the things that I need in order to simplify this expression. Putting it in a box to draw your attention to what we've done, because I need more space on the board and I'm going to have to erase that entire box, but I want to make sure that whatever is written in the box you have written down so that you can use this trick again and again whenever you need to use it. Now here's what I'm going to do. This common denominator, I'm multiplying the top by the common denominator, I'm multiplying the bottom by the common denominator, and I'm going to distribute the common denominator to each term in the numerator and to each term in the denominator. Voila. And son of a gun, something great is going to happen here. I have a factor of 3 plus x on top, a factor of 3 plus x on the bottom. They cancel. In this term, I have a factor of 3 on top, 3 on the bottom. They cancel. Nothing cancels down here, but that's okay because I really don't have a fraction. Now let me just pick up the pieces and see what's left here. Here, I just have 3. And here I have 3 plus x. And the bottom, well, the bottom is what the bottom is. Now, before I go any further, let me just point out what we've accomplished. By multiplying the top and the bottom by a common denominator, and by the way, we can multiply the top and the bottom of a fraction by the same non-zero number, can't we? This thing divided by this thing is just 1. So what we're doing when we multiply top and bottom by the common denominator, essentially we're taking this thing and we're multiplying it by 1. If we multiply something by 1, we don't change the value of it, do we? So multiplying top and bottom by the common denominator, we don't change the value of the expression because we're multiplying by 1, but we change its appearance. Once we cancel out, notice what we get. We get a quotient that is not a complex fraction. There are no fractions in the numerator, no fractions in the denominator. So this trick that we pulled by getting the common denominator and multiplying top and bottom of a complex fraction by the common denominator, that trick accomplishes changing the appearance of the original expression into a fraction that is not a complex fraction. This thing right here, it's equivalent, it's equal to the original expression. The only thing that's different is the appearance. It no longer has the appearance of a complex fraction. And that's good. We're not spiteful people, but we hate fractions, let's admit it. And I can do a little bit more simplifying in the top. Three minus 3 is 0. And this negative sign distributes to the x. So what we have left on top is negative x. Oh, look at this. We have a common factor in top and bottom. Cancel, cancel, cancel. We can cancel top and bottom by x. We can divide top and bottom by x. That gives negative 1 on top, positive 1 on the bottom. You know what? If we plug in here, we're not going to get 0 by 0. And that really was the main problem when we started out. Yeah, we had a complex fraction. But if we plugged in 0 for x here, we get 1/3 minus 1/3 is 0 on top, 0 on the bottom. And then we'd have to go to step 2 and cancel out a common factor, but that's hard when we have a complex fraction. Here, by changing the complex fraction into a regular run-of-the-mill ordinary fraction, we canceled out the 0 factor right there, and we're left with something that we can compute the limit of by plugging in what x is approaching. X is approaching 0, let's plug in 0. Well, son of a gun, that is our answer. Study this exercise for a little bit and then go back and try to work it without looking at the video. If you still get stuck, take a peek at the video and see where you're getting stuck, and then stop the video and work the rest of it. Do this a couple of times until you can just work straight through it without looking at the video. Next exercise. We have this symbol here and here that we might not be familiar with. And normally I wouldn't belabor the point, but we're going to be seeing a lot of this character in just a little bit. So it's to my advantage to milk this opportunity for all it's worth and introduce you to this symbol. Delta X. This thing is the Greek letter delta. And I think you know what X is. Those of you who have had some chemistry before, maybe you had some in high school, you may have had delta capital T. Or you may have had delta capital P. Delta X has a similar context. Delta X represents the change in X. If the initial value of X is X of 0, and the final value of X is X of 1, then the change in the value of the variable X is delta X, which is the final value X of 1 minus the initial value X of 0. And let's look at this a little bit less abstractly. Suppose the initial value of x is 3 and the final value of x is 9. Then the change in the variable x, delta x, is the final value minus the initial value, which equals 6. So delta x has the same kind of context that delta capital T has in chemistry, if you've had high school chemistry. Delta capital T, that's change in temperature. Final temperature minus initial temperature. Delta capital P, change in pressure. Final pressure minus initial pressure. Delta x has exactly the same meaning with respect to the variable x. There are some comments or some observations that I'd like to make before we actually go ahead and work this exercise. The first thing that I'd like to comment on is that delta x is not delta times x. This is not delta times x. Delta x is one indivisible symbol. Just like, well, delta x is a variable. Just like x, y, and z are variables. So this is not delta times x. It's one indivisible symbol. And because of that, if we have delta x over x, we can't do what I'm about to do. Oh, x up top, x on the bottom, I'll cancel both of them, and that gives me delta. We can't do that. And the reason that we can't do this is because delta x is not delta times x. If this were delta times x, yeah, we could cancel the x's in top and bottom. But this is not delta times x. This is delta x, and it's one indivisible symbol. Just like x is an indivisible symbol, y is an indivisible symbol. I can't take this part of the x away. It's one indivisible symbol. So delta x is a variable, an indivisible symbol, just like x, y, and z are variables. So if we see delta x over x, we can't cancel the x's. If you want to make me mad, try this sometime. If you don't want to make me mad, remember that we can't do this because delta x is not delta times x. Now that I've introduced us to delta x, and it may seem like I've been acting like a fanatic, but for the next month or two, our entire world is going to be revolving around delta x. So we're going to have to get comfortable with this. We're going to have to know exactly what it is. So now's the perfect opportunity to be introduced to delta x. Now on with the exercise. On with the exercise. What's the first thing I try? Well, I try plugging in. And before I try plugging in, let me make it clear to myself and everybody else what it is I'm going to be plugging in for. What is it here that's approaching 0? It's delta x that's approaching 0, right? So we're going to try to compute this limit by plugging in 0 for delta x. This doesn't say x is going to 0, does it? So x we're going to leave alone. Delta x is going to 0, so every place we see a delta x, we'll plug in 0 and see if that gives us something that doesn't yield division by 0. So we try plugging in. Limit as delta x goes to 0 of 2x plus 0 minus 2x over 0. It's not looking good already. Whoops. I don't need this, do I? I'm plugging in, so I don't need to write the limit in front. But what I have is 2x minus 2x, which is 0 on top, and 0 on the bottom. Okay, step 1 didn't work. We can't compute the limit by plugging in. But there is some good news, and here's what the good news is. The fact that we have 0 on top and 0 on the bottom tells us that step 2, canceling from top and bottom, is probably going to work. The fact that we have 0 over 0 tells us that step 2 is almost certainly going to work. So that's what we're going to try next. Before I can factor and cancel, I think I'm going to have to simplify this expression a little bit first. So I'll rewrite it. And I have 2x plus 2 delta x minus 2x all over delta x. And a rather nice thing happens. I have 2x minus 2x, they add up to 0. So here's what I'm left with. Two delta x over delta x. And remember, I haven't canceled the common factor out of top and bottom yet. And in step 2, that's what we aim to do. In step 2, factoring and canceling, we cancel a common factor out of top and bottom. And here's that common factor, delta x. Delta x up top, delta x canceled in the bottom. So what we're computing is The limit as delta x goes to 0 of 2. And I don't know if we've covered this topic in our other lectures yet or not. But what we have here is the limit of a constant. As delta x gets closer and closer to 0, what value does 2 become arbitrarily close to? And you're scratching your head and saying, what value does 2 become arbitrarily close to? 2 is 2. It's a constant. It's not approaching anything. It equals 2. Okay, so as x approaches 0, the only value that 2 can become arbitrarily close to is 2 itself. As x goes to 0, 2 is arbitrarily close to 2. So the limit of 2 as delta x approaches 0 is 2. Our limit is 2. And there is something else that I want to take away from this exercise. We may have already covered this in one of our lectures. If we haven't, we will. But since we've been exposed to this fact, let's just make the most of it. Here we were computing the limit of a constant 2. And that limit turned out to be the constant 2 itself. This is always the case whenever we compute the limit of a constant. So let me erase a little space on the board, and let's acknowledge this fact, even though we may have been exposed to it already, or if we haven't, we'll see it again in our lectures. But since we saw this fact here in this example, let's just make sure that in retrospect, we take this fact away with us. The limit of a constant equals the constant itself. And here's our takeaway point. If k is any constant, then the limit as x approaches whatever of k equals k. The limit of a constant equals the constant itself. The limit of a constant equals the constant itself. So let's make sure that we remember that point. Okay. We know something about delta x now. So let's just go ahead and work this exercise that involves delta x. The exercise is fairly relevant because in the next section or a couple of sections after this, we're going to be doing examples like this, and for very good reason. We have a good reason to know how to do exercises like this. And there is a little bit of a landmine here that we need to dodge. So let's go ahead and work this thing. Here's one of the landmines in this exercise. Let's make sure that we see it before we step on it, okay? What is it that's approaching 0? Is it x? No, it's delta x. So to compute the limit of this function as delta x goes to 0, what are we going to plug 0 in for? Are we going to put a 0 every place we see x? X isn't going to 0, is it? Delta x is going to 0. So wherever we see a delta x, that's where we plug in 0. What do we do when we see an x? We just leave it alone. We don't do anything to it. Okay, we dodged that landmine. We're looking good. We plug in 0 for x, so we have x plus 0 squared minus 2x plus 0 plus 1 minus x squared minus 2x plus 1 all over 0. Ooh, not looking good. Not looking good, but let's keep on with this and let's see how this works out. X plus 0 squared, that's just x squared. X plus 0 is just x, so this is minus 2x. And then we have a plus 1. And in parentheses, x squared minus 2x plus 1. Well, let's see. X squared minus x squared is 0. Negative 2x minus a negative 2x is 0. 1 minus 1 is 0. Son of a gun. We got 0 over 0. So that's bad news, but kind of good news too. It's no good. It's division by 0. That's the bad news. The good news is not only do we have 0 in the denominator, we have 0 in the numerator too. And what that indicates is that step 2, factoring and canceling, is almost certainly going to work. So let's go to step 2. As we just observed, factoring and canceling should work because we got 0 over 0 in step 1. And I know you probably don't like the way that I spell canceling, but you know what? Even if the dictionary says this is wrong, I like it better than the way it looks if I only have one L. Boy, talk about people who are set in their ways, huh? Okay. Well, in order to get a common factor, I think what I'm going to have to do is simplify the top. I'm going to have to square this out. And notice what I have. I have the sum of two things squared. And when I have the sum of two things squared, here's what I get. I get the first thing squared, and I get the second thing squared. And do I need to square that delta too? I don't, because remember, delta x is one indivisible symbol. When I put this 2 up here, this is delta x squared. So I get the first thing squared, the last thing squared, And then I get the first thing times the second thing doubled. I get 2 times the first thing times the second thing. So that's what I get. And here, I think the only thing that I can do here is just distribute the negative 2 inside the parentheses. So I'll get negative 2x minus 2 delta x plus 1. And what the heck, I think I'll distribute the negative sign inside this set of parentheses too, so I'll get negative x squared minus a negative 2x minus 1. And on the bottom, we got our old friend delta x. And something interesting is going to happen here. Yeah, a bunch of terms are going to cancel out, but there's going to be somewhat of a pattern to how this happens. Notice that I have x squared here, canceling with negative x squared here. Notice I have negative 2x here, canceling positive 2x here. And I have 1 minus 1. Now, what's significant about this? Let me rewrite it, removing all of the dead soldiers here, and let's clear out the rubble and let's see what's left and see if we see something significant. And we have 2x delta x plus delta x squared minus 2 delta x. Let's see, is that it? I think these are the only 3 terms in the numerator that survive. Now look at what we had and look at what we end up with. Do you notice anything that seems like it might be more than just a coincidence? There are a couple of different ways that we can express this. One thing is we can say all of the terms that had a factor of delta x survived. So after we simplify, the only terms that survive are those terms that have a factor of delta x. We can also say something else. Look at all of the terms that got wiped out. X squared, 2x, 1. None of the terms that didn't have a factor of delta x survived. The terms that survive the simplification are exactly those terms that have at least one factor of delta x. And if we get to this point in the process, and we're going to be doing this a lot in the week to come, if we get to this point where we had 0 over 0, and then we simplified and cleared away all of the debris, if we get to this point and we have a term in the numerator that doesn't have at least one factor of delta x, that's a pretty good sign that we've done something wrong. If we've done this kind of exercise correctly, all of the survivors should have at least one factor of delta x. And guess what? The bottom has a factor of delta x too, and that's exactly the factor that we want to cancel out. This is the factor, delta x. It becomes 0 as delta x goes to 0. This is the factor common to both top and bottom that made both the top and the bottom equal to 0. This is the troublemaking factor. This is the one that we want to cancel out. So I'll factor out delta x. I factor one factor of delta x from each term in the numerator. And I cancel this factor with the factor of delta x in the bottom. Whoops, over 1 maybe. This is what we have left. Now that we've canceled the troublemaking factor, let's plug in. And what do we get? We plug 0 in for delta. We plug 0 in for delta x only. X we leave alone. So we're going to have 2x plus 0 minus 2. And that equals 2x plus 2. Hold the phone just a minute. I was about to write out the answer. Well, I did write out the answer, but I don't think I like what I wrote. And I'm not sure where my problem was. I think it was a copying error. But from here, we take the terms that survive, 2x delta x plus delta x squared minus 2 delta x. When I did this before, I don't know if I had a minus sign here or not. It should be a minus sign. And then I factor out delta x. Remember, when we get to this point, all of the surviving terms have a factor of delta x. So we factor out that factor of delta x, and we have 2x plus delta x minus 2. This should have been a minus 2. I'm not sure if perhaps I wrote it down wrong and had a plus 2 here, but this should have been a minus 2. And we cancel our delta x's. If this was a plus 2 before, it should have been a minus 2. But we plug in delta x. We plug in 0 for delta x. And this is the only place we see delta x. And yes, I did have here, I remember clearly, now plug in. And what am I going to plug in for? Delta x. That's what's approaching 0. So I'll leave 2x alone. 2x plus delta x, which goes to 0, minus 2. This should be a minus 2. somehow this wound up being a +2, and when I was erasing the board, I noticed that it wasn't quite right. And here, enshrined in all of its glory, is our answer. And work this out a time or two. Make sure you can do it. By next week at this time, we're going to be doing a lot of exercises exactly like this. So if you get some practice doing this exercise, it'll make next week that much easier.